Hello everyone. This is our second video on 3D printing where we are going to talk about some common technologies of 3D printing and some of the material used, specifically in the most common technique called fused deposition modeling. So there are three real major technologies in 3D printing. And here I also mention a fourth one, polyjet or material jetting. There are other types of material 3D printing technologies too, like lamination and so on, using laminates. But I'm not going to go and talk about them because they are essentially different from 3D printing. So these three or maybe say four major technologies in 3D printing are fused deposition modeling or FDM, which is the most common one, followed by stereolithography or SLA, which you might call resin printing, followed by powders, which we call powder bed fusion, like SLS or SLM or electron beam forming or melting. And then, as I said, the jetting, material jetting. So what are these? The most common one, the cheapest one, that is the technology that you have and I have in our home 3D printers. It's called fused deposition modeling. Okay, sometimes FDM, sometimes called FFF. And it is the most common, the cheapest technology, although it's not the earliest 3D printing technology. The earliest is actually the SLA technology, but this FDM is what you see almost everywhere. And the base of it is you have a spool of plastic that is what we call a thermoplastic material, which is under heat. They would go under plastic deformations and you can form them. So you have a motor at the hot end, right, at the head or extruder. And in the extruder, this motor is going to pull in through a gear mechanism. It is going to pull in the spool and then brings it to the hot end, where the heating element is going to bring that plastic almost near the melting temperature, a little bit below that. And then this almost molten plastic, which is highly deformable, is deposited on the print bed for the first layer and then on the top of the previous layers for the other layers. So the molten plastic, almost as I said, is deposited layer by layer on the top of each other, and they are cold welded on the top of each other. Okay? And this cold welding will cause the material to have a rough finish unless these layers are very, very thin layers, so you cannot see those layers with naked eye without a lot of attention, really. Most of the time you see this layer by layer nature, which makes the material anisotropic, which means the mechanical properties of the material are not the same in different directions, and typically in the direction of the print, which is the z-axis or upward. In this direction, if I want to draw you an arrow, in this z direction, typically you have the weakest mechanical properties of the material, and these layers can come easily off each other, like what you can see here, and it's called delamination. Okay, so if you want to improve on that, you have to make the layers basically a lot smaller. So bring down what we call the layer height or layer thickness, which significantly increases the print time and still does not make the part isotropic, just reduces this basically layered surface finish of the object, make it a little bit more pleasant looking, and probably a little bit stronger in that z direction, but again, definitely on isotropic. So There are so many printers working based on this technology, including the Prusa, including MakerBot, including Creality, and Stratasys, many of the Stratasys printers, so many other printers that are working based on this technology. Not that these companies do not have other forms of technology like SLS or SLA, they do, but these are their most well-known printers, are FDM. Now, the plastics that you typically use in the FDM, the most common one that you see in daily life is called PLA, or polylactic acid, which is really a biodegradable material. It is based on starch. It's starch based, so it's biodegradable. That's the good thing about it. That's the cheapest almost plastic. It prints kind of the best out of all other plastics. You can print it on a printer for which this print bed here is not heated, because the adhesion of it to the bed is relatively good and it doesn't warp during printing most of the times. If you have, even if you do, you can, because the bottom of the print is quite wide and narrow, with low thickness, then you can, well, we'll talk about it in future videos. You can add glue sticks, you can add tapes, you can use hairsprays and so on and keep it to the bed. But this is the cheapest plastic. The surface finish of that is relatively good. It's the easiest to print and it's really good for decorations and non-functional parts. Okay. The major problem with PLA is specifically most of the time when we don't print our parts completely solid. That's another topic we're going to talk about later. We use infills and the inside of the part is hollow. This PLA is really weak against impacts. So if it drops from your hand and the part is heavy or it's not really reinforced or something, it easily breaks, okay? Also against heat, when the temperature goes up a little bit, it starts to lose its shape tolerances and so on. So again, it's really good for parts that are not functional, mostly decorative toys, stuff like that. Okay, for parts that are not really under a lot of heat or mechanical stress, it is relatively good. The next level of plastic is ABS, which is completely petroleum based. And this plastic is a little bit stronger than PLA, and it can tolerate more heat. And despite that, against UV light, it is weaker than PLA. One of the bad things about ABS is, although it gives lightweight parts stronger than PLA and more heat resistant, one of the bad things about it is during the print, it releases some fumes that are absolutely not good to inhale, okay? And there are a lot of research and study on it. So I absolutely recommend, if you ever want to print ABS, you make sure your printer is enclosed, okay? So your chamber is completely sealed, no fume, nothing comes out of it. And plus the bed is heated, because if it's not, it will easily deform and peel off the bed and warps during the print. So you need a heated bed and you need an enclosed chamber if you ever want to print with ABS. And definitely, as I said, it is not biodegradable. It is a chemical material, and but it is a little bit more functional than PLA. It melts, and its printing temperature is a little bit higher than PLA, not significantly higher. And later we'll talk about the post-processing of the parts printed with PLA and ABS. With PLA, typically use sanding and painting. With ABS, we can also use acetone to post-process it and make it smoother. Now, if you want something that is similar, before I go to PETG, similar to PLA, ABS is, as I said, it's a little bit stronger, more impact resistant, but again, it's not like super strong. Okay, its toughness is not uh, like super high. If it falls out of your hand, there is a good chance this one also breaks, especially if it's not completely solid. If you want some part that is a little bit more flexible yet strong, so it's a little bit mechanically maybe better than both of these, that's PETG. Okay, and PETG is also a polymer. It's not biodegradable really. And the good thing about PETG is it is food safe. Okay, unlike ABS, this one is food safe. This is the kind of plastic you see in the water bottles. Okay, when you get these water bottles from any vending machine or anywhere, right, the stores, most of the time the plastic used in them is PETG. Of course, they are not 3D printed. Okay, they are typically created by vacuum forming or injection molding or other methods, but PETG is one of those materials. It's a little bit heavier than PLA and ABS, and its surface finish is most of the time looks a little bit better than both PLA and ABS. Now, the better thing it has also with ABS and PLA is with humidity. PLA and ABS are not so good in humid environments. They absorb humidity and they lose their shape easily. PETG is a little bit better than that. Okay, so it has some good properties that are appreciated by many people. And the price of it is also comparable to PLA and ABS. These three are some of the cheapest plastics out there. There are other plastics. One of them is TPU, TPE, and sometimes they might be called flex. These are the flexible plastics. These are the ones that you can make flexible material from, and they can make so many nice parts, like what you can see here. This bottom adjustable wrench is made of PLA, this top one made of TPU, and you see it can easily be bent and deformed. So this TPU has a bunch of applications. It's an interesting plastic. The hard thing about TPU is typically the ease of printing. TPU is a hard plastic to print. The flow of it is not nice. The temperature for printing it is quite higher than ABS, PLA, and so on. So it is printed at a higher temperature. And the flow of it is not nice. So if you want to print smaller details, that's where TPU is not going to be the best. So don't count on printing small details with TPU really, because the flow of it is not nice. It's not the easiest plastic to print. But it has really nice mechanical properties, very flexible. Nylon is the plastic that is amazing in terms of its toughness. It can really absorb mechanical impacts, and it also has a good strength and flexibility, good, relatively good resistance against heat and abrasion. It doesn't release odor, and it is also food safe. So it's an amazing plastic. It's a little bit more expensive than ABS and PLA. The major problem with nylon is this guy absorbs humidity a lot more than any other plastic. So if there is a little bit chance of humidity, this guy is going to deform so badly. So this plastic is, and the PLA and ABS too, but this one specifically is the one that, as I said, we call it hygroscopic. Okay, so let me write it for you somewhere down. So we call it hygro, not hydro, hygroscopic. So it absorbs humidity. And as I said, this one is the one that is hard to print. TPU is a little bit more expensive than ABS, and PLA. Nylon is a little bit more than that. Then we go to plastics with specific properties. One of them is polycarbonate, or PC, an amazing plastic that has very good strength and temperature resistance. And it also absorbs humidity from the air, not as bad as nylon, but it's very good. in the helmets of astronauts, this is one of the plastics that they use mainly, polycarbonate. Okay, this is a really amazing plastic that you can print. Let me tell you a couple of other things before I jump to carbon fiber. Many times they combine this PC and ABS together and they make something called PCABS. Okay, which is a really good plastic. There is also another plastic similar to ABS. It's called ASA, and this is a little bit stronger and has better mechanical properties compared to ABS. So ASA is something similar to ABS but better mechanical properties, and there is PCABS that is superior to both of them, both PC and ABS. So there are other plastics like alloys of these plastics, right? Like combination of these plastics that you can see in the market. The next plastic we have is called carbon fiber, which is not really the spool itself entirely. It is typically small carbon fibers that are inside, they are placed inside another host plastic, like inside PLA or ABS or so on. So it's not really entirely carbon fiber. There is PLA inside the PLA. You have this carbon fiber. So the plastic itself the spool itself is like a composite basically. And you print that, and that gives the parts a very high strength, at the same time very light weight, and you can use it for functional parts which are under stress, yet you don't want them to be very heavyweight, like parts of, they use it for bicycles and so on. So this is an interesting part, polycarbonate. And then if you want to go to much higher level plastics, high performance plastics, are these two guys, PEEK and Ultim. These are what we call high performance plastics, and much more expensive than any other plastics, especially PEEK. For example, let me just give you a comparison. 1 kilogram, so 1 kilogram of PLA you typically can buy from Amazon or some vendors about between 16 to 20 bucks. Right? That's what you typically buy. In the meanwhile, 250 grams, 1/4 of a kilogram of PEEK, if you can buy, it is about $350. Okay, so 1 kilogram of that is going to be $1,400 compared to $16 or $20. So you see, it's something in the order of 100 times more expensive, 80 times more expensive than PLA. And you might say, well, that's just a plastic. What makes it such expensive plastic? Well, it's the mechanical properties. PEEK, if it's printed properly and you have a good printer, can show mechanical properties comparable to aluminum. I mean, the mechanical strength of it could come close to aluminum, like half of aluminum or so, close. And the melting temperature for this guy is like 650 degrees Fahrenheit. Okay, and as I said, close to aluminum, like half or a little bit more than half aluminum yield strength. Ultim is a little bit not as high performance as PEEK, but it is close. It's like the next level option if you don't want to get PEEK. So PEEK is like the ultimate plastic, really, at least the one that I have seen so far. And you have to have a specific printers to print this with very high temperatures. It is very sensitive to humidity, so it should be enclosed with specific conditions. The adhesion of that to the bed is not so good. So you have to have a lot of things under control so you can print peak. But if you can, guess what? It gives you part that strong, that resistance to temperature, and guess what? You can machine parts out of peak. So if you have a 3D printed part from peak, you can put it in the lathe machine, in the milling machine, in the CNC machine, and you can machine them. Okay, that's why you use this plastic in advanced aerospace industry for prosthetics and so on. Okay, so it can literally replace some metals in that area. Okay, as long as it is printed properly. So we have this range of plastics called high performance plastics, and they have their own specialized printers. What else do we have? Well, some of the other things we have are we called, let me jump to 10, then I come back to item 9. We call them exotic plastics. These are also very interesting. I love these plastics for what they have. And you might say, like what? Well, they have particles in them that make the appearance of them look like wood or metal. Really? Yes. If you look at these two here, this one has basically, I guess, silver particles, if I'm not mistaken, and this one has wood particles. So when you print them, they absolutely have a different surface finish that looks like wood or looks like metal. Okay, and there are other ones that have like not real gold particles, but the appearance looks like gold, the appearance looks like bronze, like copper, like steel. This one, I'm not sure if it's silver or steel. There is a chance this one is steel, so I think it is the steel one. There are some that looks like they are like out of concrete or ceramic and something. So they are amazing in terms of decorations. There are some that are glow in the dark, and I really love these plastics like this one. Okay, so they glow in the dark and mostly under UV light, but in even if the UV light is not significant, they still glow in the dark. There are some of these spools that are not exotic, but they have multicolor. So through the length of the spool, the color of the spool changes. So when you print, they give you a rainbow kind of color. One of the ones that I really like is this guy, Conductive. And the conduction by them is typically done through the carbon fiber through them. So these guys really conduct electricity, although the amount of loss through even a short length of the wire or the circuit is significant. So, but they really can turn on some LEDs. So if you put your battery on the positive and negative kind of path and connect LEDs, they can definitely turn on LEDs. Okay, and I have done the print with all of them, so it's not just like I have seen them somewhere. I have samples of each and every one of these parts in my office and at home. So if you want, just give me a feedback next time I show you sample parts. I bring maybe this conductive plastic and I'll show you. I turn on an LED for you. Okay, so you cannot really replace a printed circuit board or PCB with these guys because, as I said, the amount of loss for them is really large. But if it's something small, then yes, you might be able to 3D print a PCB instead of mill a PCB. Okay, so they have their amazing applications. So these are just some of the plastics, and then there is one category of plastics here that I call support material. These are not the model material, so these are different from the items 1 to 10. And these are to support the weight of overhangs in the parts, right? And that's one of the topics that you'll see in the next video. When you're trying to print overhangs, okay, then you need something called a support material, which you can see here. So when I try to print something, since these plastics are put on the top of the bottom layer, if there is no bottom layer, you cannot just put these layers of plastic up in the air. You have to have something below them to carry their weight. So you print this extra plastic called support plastic. And sometimes the support plastic is from the same material that the model is printed from. Sometimes it's from a different plastic. So here you see clearly the support is the same resin as the part is, but here the support material is different. The model material is white. So this is the model plastic, which could be like ABS or ASA. And this brown one here is the support plastic, which could be like HIPS or QSR plastic. And what's the difference between these two plastics? The difference is this. When you put the printed part, this whole thing, when you put it into a solvent, a chemical solvent, then that solvent would only attack the support plastic and eliminates it, but has no effect on the model. So you chemically remove the supports and keep the rest of the part intact with a nicer surface finish without the need for you to use clippers or long nose pliers and break the support and leave scars on the part. Okay, so that's the advantage of these support material is separation of the support from the part can be done chemically without mechanically breaking them and possibly breaking the parts or leaving scars. So that's called the support plastic. And there are a bunch of different ones, like for ABS, ASA, and some other plastics. We typically use either HIPS or QSR. And then the solvent that we use is typically the chemical that we use is an alkaline, like the lye bath, or most of the time it's not real lye, it's another type of alkaline material, like for example the one we have in our lab, we call it the Lamination. Okay, and this PVA is another support plastic that we use for PLA. So this one we use for PLA. These two, as I said, we use like for ABS or ASA or so on. The good thing about this PVA is the solvent for it is water. Yes, really. You put the PVA and PLA both in water, and water will get rid of PVA for you. Okay, so there are support material that can be dissolved in water, like PVA. So, and although they are just going to go away ultimately, but it doesn't mean they are any cheaper than the model plastics. Okay, they are typically the same range of price as the plastic, if not more expensive. So this support material is another type of plastic we have in FDM. Good. So I guess I told you a bunch about FDM, and it's time to switch to the other technologies. But before that, I just want to show you this comparison chart briefly, which shows some important properties of FDM plastics and some of the most well-known plastics in the market: PLA, ABS, PET or PETG, nylon, TPU, and polycarbonate. So for each one of them, there is a color, a dot, and then there are, as you can see, 7 important properties: ease of printing, visual quality of the printed part, the maximum strength of the material, the elongation at the break, so how much the part can be elongated or deformed before breaking, how much it can resist against impact, or what is the toughness basically, how good does it attach to the print bed, and how much does it resist against heat. So clearly you see PLA is not really the best when it comes to heat resistance, and definitely against impact is the weakest material. But it's the best when it comes to printing. Visual quality of it is typically the best, and the layer adhesion of that is the best. Now here it shows PLA as being stronger than ABS, and nylon and everything, which I do not completely agree with. So this is not really necessarily the ultimate table. So I kind of disagree with this. PLA comes probably here or here in terms of the maximum stress it can tolerate. So I do not, based on my observations, I do not really think the PLA is much stronger than let's say PET or ABS. I don't think so. PC is definitely the strongest of them in terms of mechanical stress that it can tolerate. I do agree with that. This is absolutely correct. And then it says, for example, TPU is, of course, the one that can be elongated the most. Of course, that's a flexible plastic. And if you hit it, almost nothing is going to happen to it. It's extremely tough plastic, right? But as you can see here, that's the hardest plastic to print, right? And the nylon is hard to print in terms of layer adhesion, followed by ABS. You definitely need heated bed and so on and so forth, right? So you see some of these important properties, as I said, except for this, most of it is relatively correct. It does depend on what kind of plastic you are buying from which company, and it's not a general thing for each and every one of PLAs and ABSs in the market, but to a high degree of accuracy, I would say most of this table is correct. Okay, the second technology of 3D printing is called stereolithography, or SLA, and that's the first 3D printing technology that ever came to market. There is a newer version of it, which is called digital light processing, or DLP. The technology here is based on resins, the resins that are photosensitive, or photopolymers, basically what we call. So the technology here is exactly the opposite of FDM. In FDM, you pulled in a spool of solid plastic, you almost melt it, and then put it layer by layer on the top of each other. Here is the opposite. You have a tank of liquid resin, you shine a UV laser on it at specific locations, and as soon as the UV laser comes in contact with the resin at that point, it what we call solidifies, or we say it cures the resin. Okay, convert it into solid. So then by moving the location of laser shining on the resin, you build these layers on the top of each other and make the part. So the laser source comes here, it goes into mirrors. These mirrors are typically called galvanometers or galvos, and they basically change the direction of the exiting light, right? So they can move very fast and shine the laser at different pixels, different locations, and make your printed resin parts or cured resin parts. And a few things about this is one of the most famous resin printers. It's called Formlab Form 2, okay, which we have in our lab. It's a very good, reliable printer. It has some limitations on other things that we are going to talk about, but one of the things is when you print this part, typically your resin tank is down here. And then when you print the part is printed upside down. Okay, so this is like what? This is like the bottom of the part. And it comes out of the resin tank first, and then as this, basically the print bed goes up, right? It is going to bring the bottom of the part out, and then the top layer, and the part is printed upside down. Okay, in most of the resin printers, that's what happens. What else? When you print a part, typically you don't directly get it out of the printer and use it. Why? Because most of the time there is a little bit of resin that is not completely cured left on the part. And these resins most of the times are going to cause skin irritations for you if you touch them. So when you print with a resin printer, you want to have basically personal protective equipment, or PPE, specifically gloves and goggles, okay? And most of the time overalls, right? Or you might call it coveralls. And you don't want them to touch your skin or get into your mouth or nose or something. They are not safe. They are environment hazardous material. And when you bring that, as I said, there is some uncured resin on the part. So the next thing you do, typically, you take this part and then you put it in a second container, which is called the wash machine. Okay, so it tries to get rid of the uncured portion of it. And you might say it washes that printed part using what? Using water? Absolutely not. It's typically inside it is what we call isopropyl alcohol. Hopefully I wrote it properly. So it is alcohol, and alcohol gets rid of the uncured resin, and then you remove the support material. Okay, because this type of print also needs support, and I showed you a picture of it. That's what you can see here. So you break this part, okay, try to get rid of it. And then once you do that, then you put it in the further cure machine. And in this machine, you make sure that everything is completely hardened and there is nothing in it that is not completely cured. Okay, if you don't have this machine, you can just put it under sunlight and the sun UV light will cure it for you. But most of the resin printers, they come with a wash machine and with a cure machine. Okay, so, or you have to buy them separately, but they are a part of a resin printer. Now, there are all sorts of resins that you will see. There is rigid resin, there is flexible resin, correct? So the types of resins that you see, as I said, there are lots of different types of resins. We have rigid resin, we have flexible ones, and we have the ones for dental procedures, which are most of the time the type of rigid resin. We have the type of resin we call high temperature resin, which is really good for applications where there is a lot of temperature and so on. So there are lots of different types of resin, and depending on the type of resin you use, the mechanical properties of the printed part will vary significantly. And many times the resin parts are transparent, sometimes they are not. So you can see sometimes they are kind of semi-transparent, you can see a little bit light through them. Sometimes they are completely opaque, and use them in many medical conditions as well, and like dental applications for crowns, for teeth models, and so many other things. The major advantage, as we'll discuss, the major advantage of resin parts is they're great, unparalleled surface quality. The surface quality of the parts made of resin is extremely nicer and smoother than parts with FDM, because the resolution, the layers that they cure are far thinner than the FDM layers. Okay, so the parts with resin, you can print very, very small details. You can print extremely nice, smooth surfaces. But at the price of resins are much more expensive than FDM plastics. So for example, for this Form Lab, I can tell you, like, we buy 1 liter of any of these resins, it is around $190. Okay, and most of the time, the thing with the resin is this: when you open up a cartridge and pour the cartridge into the tank and use it, it's not really the way to pour the rest of it that is not used back into the tank. You have to use as much of it as you can, and then the rest of it, if you cannot use, will be wasted. So if you want to switch to another one, you're not going to pour it back into the cartridge unless you have separate tanks, and that's what many of us do. We buy separate special tanks inside the major printer tank, So we try to take that whole thing and store it, not pour it back into the container that it came with. And again, still, even if we use that special tank and put it back into the cabinet, they have a specific life, which is typically at max 6 months or so. So the life of resins is far less than the FDM plastics. FDM plastics, if you keep them in a dry environment and away from the sunlight, they can live quite longer than resin. So resin in general is more expensive. The material is biohazardous and it has to be cured and handled properly. And if there are waste material like this, you're not really going to throw it in the trash can, okay? Because they are not biodegradable. You have to safely dispose them based on the environmental regulations in your area. So resins are really specialized for special applications, and they are not really meant to replace FDM for regular applications. Good. Let's go to the next category, which is called basically powder bed fusion techniques. In the powder bed fusion techniques, there are a bunch of categories, but the three main categories are SLS, SLM, and EBM. SLS stands for selective laser sintering, SLM is selective laser melting, and EBM is electron beam melting. So what's special about this? So what you have here, you have basically a powder container. So here you are dealing with powder of the material. So it is powder of solid material, not like FDM that you deal with spools. Here the material is pulverized already, it's in powder form. And then the powder is is going to cover one layer on the print bed. So there is basically an arm that grabs enough of that powder and then brings them onto the print bed. And then here you have CO2 laser, and then again you have these galvanometers that will shine the laser at the places that you want the powder to be sintered or melted together. So you have all of these powders right on the bed, and then laser is going to target a specific area. Let's say laser says, hey, I want this area, I want to focus on that. Shine the laser and makes all of these powders to what? To get fused together, to get molten or sintered together, and makes that solid part. And then again, this arm comes and grabs one more layer of powder, and it is built layer by layer on the top of each other. Okay, so that's what we call the recoater. Now, this technology, it has pros and cons. One of the major pros of that is it can print metals, okay, because you can convert your metals into powders. You can convert your metals into powder. So this is the technology for printing metals. And then the other good thing about it is with the SLS method, not SLM, with the SLS method, the material that is below your current layer of powder serves as the support for it. So you really do not need this support material. When you print with the powder bed fusion methods, you do not, with SLS only, not SLM or EBM, you can avoid using the support material, and that reduces the waste. So that's another advantage. And now, what are the disadvantages? One disadvantage is typically these machines are big machines, okay? They need side equipments and extra peripherals to operate. So you typically need a lot more room than a typical printer. and you need specific processing on the powder, like the rest of the powder that is not used, how you can recover that and filter it back into the container, how much of it you can recover. Most of the time, the rest of the powder here that is not sintered or melted, you are going to put back in the container, but not directly. You have to filter it and clean it. And you typically do not pour all of that entirely in the container. You mix some fresh, unused powder, some percentage of that, and then some percentage of this unused one, right? And you do not use this unused 100% back again into the container. Because although it's not sintered, but it has been exposed a little bit to the heat, so it doesn't have as good clear quality as the powder that comes directly out of a sealed container. So you have to mix, and it's not like there is no waste. Over time, if you don't use a lot of this powder, you will come up with a lot of powder that does not have good quality. And that's one of the reasons when you print with these machines, especially because they have big print beds, when you print with these machines, you want to print as many parts as you can. Okay, so these are typically used to print a ton of parts in a row. And that makes them suitable for industrial large scale productions. Okay, so you produce a bunch of these parts at the same time to minimize the amount of waste and accelerate the process. They are much more costly than any other printer, both to buy and to operate. For example, as I told you, a Prusa is like 800 bucks, okay? An SLA Formlab 2, for which the print size, by the way, is quite smaller than Prusa. This guy, the cost of it, Form 2, with the cure machine and with the wash machine and everything, this is about $5,000. Okay, but this guy here is bigger than 500,000 and sometimes bigger than $1 million each. Okay, so this is very costly, as I said, to buy, to run, and operate, but it gives you some capabilities like printing metal parts that by no means you can make by a CNC machine or so. Okay, and SLS is mostly for plastics and plastic powders like nylon. Most of the time it's nylon. SLM is mostly used for metals. And EBM is for, it's not like SLM is not for anything else, but mostly the machines do metal printing, they use SLM, and these guys use SLS. And you might say, what's the difference? The difference is the amount of temperature applied. In here, you're just sintering the metal powders or the plastic powders, the powder. Here, you're completely melting it. So the temperature here is higher. This one is running at a higher temperature compared to this. And this one makes the part more uniform, more homogeneous, kind of. And that's another advantage of these printers. Okay, the parts they print is much more isotropic than the FDM parts. Okay, they are much better mechanically compared to the FDM parts. And as I said, again, the temperature range of SLM is bigger than the SLS printers. Okay, so that is about SLS and SLM. And electron beamforming, instead of CO2 laser, it uses a beam of electrons to do that. So it generates more heat. It typically comes up with better surface finish, with better mechanical properties. But again, it needs its own peripherals to generate the electron beams. And you have to be careful when dealing with electron beams. You have to make sure that they are not hitting your body and causing any medical problems. So there are all sorts of other versions of these things. a couple of other things that I need to mention about FDM and SLA before I go to the last technology is this. One, here you saw I mentioned SLA and DLP, right? And I did not distinguish between these two for you. So they both work on solidifying resin. What's the difference? SLA, when it shines the laser onto the resin and solidifies, it does it 1 pixel at a time, 1 point at a time, okay? So it shines here, let me use a different color. It shines here and solidifies, then here, here, here. DLP, instead of that, it basically has the scan of that layer. It has like the cross section of that layer of the part, and then tries to shine the laser entirely together and form one layer all at the same time. So this one prints like pixel by pixel, point by point. This one prints layer by layer, and that makes DLP to be what? Much faster. Okay, so this one is the faster technology. This is the newer technology. This is much faster than SLA is. So that's one thing I wanted to emphasize. The other thing is these days there is a new technology for metal printing using FDM. Really? Yes. So what is this? Because FDM used to be only plastic, but now there are some companies like Markforged, right? That they are trying to create printers that do FDM. I guess it's Markforged, and they are what they are doing is this. They have the metal powder, like the SLS or SLM. They have the metal powders in a spool. So they have a spool, and most of the time the spools these guys have is not like a plastic like this, right? That's not the kind of spool that they use. The spools that they use, or the feed they might call it, is a rod. So it is a rod, and what's inside this rod is a bunch of what? Is all of these metal powders. And how are these metal powders are attached together or kept together? You have what? You have the bounding agent, the binding agent. So this rod here is what? As I said, it is like metal powder plus the binding agent, a gluing agent, really. Okay, that's how they keep these particles together, the powder together. And when they go into the machine, then the machine uses the FDM technology and deposits these layers of powder and binding agents next to each other on a layer, and then go up, up, up. So now you have a physical part that is a lot of binding agent and a lot of what? Metal powder. And then they put it in a furnace. Most of the times the furnace is also a part of the printer. So many times you see the printers of these FDM metal printers to be as large as your SLS printers. They are big printers. And then in the furnace, the heat will evaporate the binding agent and only leaves what? Only leaves the metal powder behind. And then they use further heat to what? To basically sinter these metal powders and kind of stick them together. So you use the heat, right, to evaporate the binding agent and sinter this powder together. Now, of course, since it's really not completely melting these particles together, or the powder, I so far have not really physically tested myself. One of the metal printed parts with this technology against one from SLM. But based on what they described to me, I'm kind of confident that, or positive that, the mechanical property of this is not going to be comparable to SLM machines. And that's one of the reasons these machines are like sold at about like 180K compared to those 500,000 and so on. That's one thing. Two, when you print and this binding agent evaporates, the part shrinks. So it's not going to print this. It's going to print, if you don't calculate how much you will shrink, you will end up with a part that is smaller and you lose tolerances. So they have software that tries to very accurately, based on their claim, calculate how much bigger you have to print this. So after shrinking, you end up with the original or intended design. Okay, so this shrinking is a big problem, and they're trying to solve that through software really, and simulations and calculations. Again, they claim really that they can replace the SLM machines. So far, I'm not positive about it. And as long as I get more testing and more data from them, I will let you know. But this is another category that they try to bring FDM to the realm of metal printing. So hopefully these guys were useful to you. The last category that I want to mention is called material jetting, okay, which really most of the time is dealing with a resin, or if they are non-resin powders, then you have something, a liquid, that is called the binder. And what this method does, the jetting printers, is if it's just the polymer jetting, what you do, you have lots of these drops of the resin that they come from all of these holes beneath the bottom face of the printer. All of these droplets, or sometimes they might be called voxels or 3D pixels, they drop on the print bed or on the previous layer, and then the UV laser selectively what? Cures them, right? Or as I said, if there are some original particles on this layer, they drop the binder droplets on them and then tries to cure the binder and those powders all together. And the good thing about this printing is these droplets that come down, or the kind of powder that they try to bind together, you could go with several different colors, so each one of them can basically drop for you a different color, right? So for example, you can have red resin coming out of this one, you can have blue resin coming out of this one, and maybe green resin coming out of this one. And by a proper combination of this, you can have multicolor and or multi-material parts. Okay, and you can see parts like this one that I showed you in the previous video. These are the parts that you can get out of a polyjet printer, right? Multi-material, multicolor, amazing demo parts, amazing surface quality also, because they are really resin printers. And they're amazing in terms of the final product and the look of the final product that they make. These polyjet printers, though, they are quite expensive. Okay, so these polyjet printers, I have seen them in practice. These polyjet printers are typically starting around bigger than or equal $200,000 to $300,000. Okay, whether it's Stratasys or HP or other printers that I have seen, they are typically 200 or 300 grand and above. So they are really meant for companies that create such high high fidelity, nice surface quality parts, multicolor, multi-material. Otherwise, they are not really meant to be used for regular people. The same thing with SLS. Now, so for hobbyists and learners and education, most of the time you deal with FDM, sometimes with SLA. We have both of them in our lab. SLS is like the next level technology. So unless you have a big research lab, there is mostly these guys to be used in industry as well as the polyjet. So the bottom two are really mostly for industry, and they are very expensive. Okay, and finally, I want to have a brief comparison of these four major 3D printing technologies for you in this table. So here I have all four methods for you, and I have six criteria here that I want to emphasize. The type of material. FDM is mostly plastic. As I said recently, they have these Markforged printers with the binding agent. I still don't believe in them, but they're trying to bring material into FDM. SLA is resin. The same thing with multi-jet. Now, it can also, in the addition of the resin, it can be like plastic too, because you have the binding agent that can fit them together. And then for SLS, SLM, it can be plastic and metal for SLM. The layer thickness for FDM is between 0.5 to 0.05 of a millimeter. Okay, like for example, Prusa on a normal mode, it is at like 0.2 mil, but it can go as low as 0.05. And for rough prints, it can go to 0.4 or 0.5. Some printers like MakerBot, they operate at 0.4. So there are all sorts of layer heights, but definitely, unless you use this very bottom one, they are mostly rough surfaces. So surface finish is rough to moderate rough. SLA and multi-jet, they start at 0.05. That's like the best you can achieve with FDM is the worst you can achieve with SLA. And then they go down to as low as 0.015. SLM goes to 0.01. So SLS and SLM, they have very, very small layer thickness, right? And the multi-jet. And so you might say, well, if SLS and SLM, they have such fine layer thickness, then they should both give me nice surface quality, and the answer is no. SLS and multi-jet, they do when they use resin. SLS and SLM, they don't. They are rough to moderate rough, or I can say moderate rough maybe. They are a little bit better than FDM, but they are still rough, and that's because of the nature of melting those particles. Okay, those powders are molten or sintered, so their shape is changed during that process. And most of the time, do they need post-processing? Absolutely, especially for metal ones. Most of the time, you see they are machined, or at least some parts of them will be machined. If they are made of plastic, they have to be sanded with this sandpaper and or painted. The same thing that you do for FDM. The way to post-process it is to use sanding, painting, using epoxy, using electroplating, using acetone. We'll talk about all of that in a separate video. For SLA and multi-jet, for SLA, we paint them if we want to get a separate color, really, but we don't need to apply much of a sandpaper because they are really smooth. And for multi-jet, we really do not need to paint them because they can give you different colors too. They act quite similar to a paper printer, but in 3D pixels, which, as I said, we call them voxels instead of 2D pixels. So the product out of a multi-jet you can directly use, really. They are so nice in terms of appearance. For SLA, if you really want to paint it, most of the time you don't. But SLS, SLM, and FDM, you definitely need to post-process most of the times, unless you really don't care about that appearance and the functionality matters. Do they need support material? FDM definitely needs. SLA does need. A multi-jet does need. Between SLS and SLM, the powder methods, SLS, as I told you, it does not, but SLM does. And finally, in terms of cost, FDM is absolute cheapest, SLA is medium high price, and SLS, SLM, and multi-jet are high. Or I can say, if I want to put it properly, I have to say very high. These two are very high cost, okay? They are really have a justification to be used only in industry and productions, not really for home or most of the time even education applications. Okay, so I guess I told you some important topics about technologies and some of the material used in 3D printing. Thank you for being with me. In the next video, we are going to go more technical and we are going to talk about the parameters involved in 3D printing, right? Like infill, shells, as I said, the support, the skirt, brim, raft, bridges, retraction, and so on. So from next video, we're going to go more into technical side of it. Thank you so much. I will see you in my next video.